Hey guys, this is Coach Lowe, and we are starting Chapter 5, and the first thing we're going to talk about will be bisectors of triangles. We're going to talk about two different things in this section. So bisectors of triangles, and this is 5-1, geometry. All right, let's get going. So number one thing, we're going to talk about a perpendicular bisector. And a perpendicular bisector is a segment that bisects a side, cuts it into two pieces, but it's also perpendicular to that side. So we've looked at this with segments and lines and rays already. If I have even a line, it doesn't really matter. I can bisect this segment that's part of the line. I can bisect segment AB. Remember, can't bisect a line because it goes on forever, but I can bisect the segment. So cutting the segment into two equal pieces. All right, so there's a bisector. That side AC is congruent to this side CB. But today we're going to talk about a perpendicular bisector, which we also have talked about before. And a perpendicular bisector bisects the segment into two equal pieces, but is also perpendicular to the segment, so forming four right angles at the point of intersection. So we're going to look at perpendicular bisectors, but we're actually looking at perpendicular bisectors inside a triangle. All right, so the first theorem that we need to look at is theorem 5-1. So you will need to look that up in your book and get that copied into your notebook. Perpendicular bisector theorem. And the perpendicular bisector theorem says if a point is on a perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. So this is kind of a cool thing. I'm just going to go ahead and make a little triangle out of this guy up here. But what that's saying is this point, this vertex here is on that bisector, that perpendicular bisector, and it's saying if I have a point on the perpendicular bisector and I draw segments back to the endpoints of the original segment, then these sides are equidistant from this vertex point back to the endpoint, and then from this vertex point back to the endpoint. The distance is the same. So that's kind of a cool thing. So that means AD is congruent to DB. And we could draw other points in here. We could make smaller triangles. We could draw those, make this F, and this distance would be the same as that distance. So kind of a super cool thing that theorem 5-1 is. Theorem 5-2 is a converse. So if I have a point that's equidistant from the endpoints of a segment, then it is on a perpendicular bisector of the segment. So if I just pick a random point out here somewhere, and the distance is the same from A to E as it is from E to B, then I know there's a perpendicular, there is, or the, I should say, not there is, but the perpendicular bisector of AB runs right through E, which it will. So that's kind of cool also. We just have all kinds of cool things going on today. All right, so let's keep moving on. Let's say that I have a triangle here. That would be a circle. Yeah, it is. All right, let's grab a triangle here. And let's just flip this bad boy around. All right, so I have a perpendicular bisector. This time it's coming from the vertex, and it does not have to come from the vertex. But I have a perpendicular bisector. So it's going to cut those sides in two equal pieces. This is A, this is D, this is B, and this is C. And this side is 8.5. Could you find the measure of BC? Absolutely. We could find the measure of BC because we know this is a perpendicular bisector. I see the 90-degree angle, and I see that these two sections are congruent to each other. So BC is 8.5. Now, here's another cool thing. If I had given you this information, We would also know that this is a perpendicular bisector because C lies on that perpendicular bisector. So we would also know that these two are congruent, which is kind of a cool thing because we have side, 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 or we have side angle, side congruence with these two triangles, which means all the other parts are congruent. I know that DAC is congruent to DBC. So let me just point that out again. I have side, angle, side congruence. So AD is congruent to BD. This angle ADC is congruent to angle BDC because they're both right angles, and DC is congruent to itself. So that would be side, angle, side. Awesome, awesome. Okay, so here's the other thing. You can draw perpendicular bisectors for all three sides of your triangle. So I have the first one drawn here. So there's one. All right, let's get the perpendicular bisector to side AC. There's two, and let's get the perpendicular bisector to BC. And there's three. All right, so let me go ahead and mark these guys over here. This side is now congruent, or that section is congruent to that one. There's the point of intersection. And this section is congruent to this one, and there's my point of intersection. These are all right angles here. This point right in the middle where, now it's not a big deal when two lines intersect. I mean, we have an intersection point, but when more than two lines, three or more lines intersect, is a super cool thing. That doesn't happen all the time. So this is called point of concurrency. And when we're talking about the perpendicular bisector intersecting, it can be in the middle, it can actually be on the triangle, or it can be outside the triangle. This is called the circumcenter. All right, so there's the circumcenter. So what I would like for you to do is try for to find, let's get a bigger one than that, to find the perpendicular bisectors of a right triangle, and then also do one for an obtuse triangle. For an obtuse triangle. These, the circumcenter on an obtuse triangle should be outside. So where those lines intersect will be outside, and this one will be on the triangle for a right triangle. All right, so try those out. So remember, in your notebook for this, you need 5.1, 5.2 in your notebook, and then theorem 5.3 is the circumcenter theorem, and you'll need that in there after you finish with this little activity over here to the right. So in your notebook, you should have these three theorems. You should have points of concurrency for an acute triangle, which is the one that we did, for a right triangle, and for an obtuse triangle. So I will be looking for those. All right, the last thing in this section, angle bisectors. All right, so angle bisectors means that we have a ray or a segment that bisects an angle. So it's going to chop it into two equal pieces. All right, so here's two more theorems that you'll need. 5.4 is the angle bisector theorem. And remember, when you get into class, if you have questions on these or you need me to walk through these with you, make sure you have them in your notebook, and then we'll put some notes in there that will help it make a little bit more sense if you're still confused about it after we talk about it in class. So make sure these are in your notebook. All right, so the angle bisector theorem says if a point is on a bisector of an angle, then it's equidistant from the sides of the angle. So let's get us a little angle going on here. All right, so here's what that theorem says in English. So I have A, B, C, and D. And this BD, ray BD, is a bisector. So these two angles are equal to each other. So here's what this theorem says. If I have a point on this bisector, then if I draw a line back that would be perpendicular here, let's see if I could get one perpendicular. on now. That looks perpendicular. Okay. That these two lengths or this distance is the same from D to this intersection point E as it is from D to this point of intersection F. That those two distances are exactly the same, equidistant. And remember, when we look at these distances, they do have to form right angles at that intersection point. That's how we measure distance, with perpendicular segments or, yeah, perpendicular segments. All right, so 5, the converse. It says if there's a point on the interior of an angle and it's equidistant from the sides of the angle, then it has to be on that bisector. So if I have a point here and this distance is the same as this distance, then I know it's right on that bisector. All right, so let's try a couple here and then we'll go to the last theorem and we'll be finished. All right, so let's get a little triangle. Well, let's do some rays again. All right, so I have, here's B, here's D, here's C, this is 5. These angles are congruent to each other. These are right angles, which is a clue, right? That's a huge clue. When I see these marks, I know that this is distance. And they're telling me that this distance is 5, which tells me the distance from B to D would also be, yeah, 5. If they gave me this angle measure, so let's say that they marked these two equal, and I didn't have this mark down here, could we find the angle measures if they gave us one? So let's say they gave us this angle measure was 31 degrees. Do I know this angle measure? Well, yeah, that's the converse of the theorem, right? If these are equidistant from each other, then I know that they are on an angle bisector. So AD is the angle bisector. That means angle BAD is 31 degrees. It's congruent to DAC. All right, so let's get this last one, and we'll build on this as I see you soon. If I have a triangle, I can draw angle bisectors through each vertex or for each vertex. So we can draw angle bisectors, and as you do this, you're going to see that they are going to intersect as well. All right, so I have angle bisectors here. Where these angles intersect is called the point of concurrency again. Cool things happen when more than two lines intersect, and these are called the incenter. All right, so where three angle bisectors intersect is called the incenter. And this really talks about a circle being inscribed in a triangle. And we'll talk about that a little bit when I see you again. And then the other one is a circumscribed circle in a triangle. So we'll look at that. That's pretty fun. Pretty good stuff. All right, so guys, I need you to make sure that you have theorems 5.1 through 5.6 in your notebook with the words, not just theorem 5.1 through 5.6, but with the theorems written down. And if you want to draw the picture that's in the book, or if you want to draw your own, totally fine with me. So that's it for section 5.1, and this is Coach Lowe, and I'm out.